Thank you, Ariane. This is a very nice introduction. Okay, where are we? I got a clicker somewhere, right? Here we go. We are here. You're probably wondering where I'm going with this. We're here in time and space. Our decisions that, as the leading global authority on what happens next in the realm of human spaceflight, have put us here. With a successful and vibrant presence on the International Space Station, but with no way today to get there from U.S. soil. And with the means to reach out to the moon, an asteroid, and Mars, but with no aligning global strategy to make it happen. And with a small host of suborbital service providers poised to blossom into the business, albeit years after we thought it would really happen, after we watched Spaceship One launch in 2003. It's not right or wrong, but it's our reality, and we are here. We could have been elsewhere. The forks in the road that put us here are a part of our space history. The dedication to lop off the last few Apollo missions. The geopolitical form of the perfect storm that led us to the moon in the first place. The decision to build a space shuttle, the collapse of the Soviet Union. Challenger, Columbia, 9/11, Constellation, CEV, and Orion, and now the SLS. The decision to pursue a fee-for-service transportation model to low Earth orbit for cargo and then crew. All events and decisions which, if they had unfolded differently, would have presented an entirely different landscape. But I think all paths would have led to an orbital outpost. It's clear what we were meant to do, and it's clearly where we were meant to be. Before we talk about where we might go in low Earth orbit, let's talk about where we might have been. Starting back when we were thinking about a permanent presence there, the Spider Station on the top left. After NASA announced the space shuttle's construction in 1970, it needed a place for a new reusable launch vehicle to go. This 1977 design known as the Spider was designed with the shuttle in mind. The concept looks like a ballpoint pen floating beneath the saucer with the bottom missing. It used a spent shuttle fuel tank pushed into low Earth orbit as the main body with a circular solar array for power. It was thought that the station could house astronauts on a stopover to other destinations. More about that later. In the top right, conceived of during the Apollo era, the large orbiting research lab is based around three small components, much in the same way that the later space shuttle would ferry astronauts and supplies between the ISS and the ground. The design used the Saturn V rocket, which launched the Apollo missions to bring a small crew to the station. Spinning designs, lower left. Because of the deleterious effects of long-term exposure to microgravity, NASA had long considered rotating space stations. Even a modest spin would provide a small amount of gravity which could counteract the weakening of muscles and other effects extended to spaceflight. Interestingly enough, over the course of the research in the International Space Station, we think we really don't need this. We can go back and forth to Mars without anything. All we have to do is exercise the right way and eat the right things. This 1969 concept rotates on a central axis and would have been assembled in space using spent Apollo vehicle stages. Most of the concepts were eventually abandoned in favor of the zero-G stations that we see today. And finally, an inflatable station on the lower right, made by no one else than Goodyear, that helped design this concept in 1961. After launch, it would have inflated like a giant rubber wheel, providing pressurized components for living and working in space. For reasons that were driven by cost, supportability, and manufacturability, we eventually settled on a modular design that's our home in space, the International Space Station. ISS agreements extend through currently 2024, but sustaining engineering studies say we can probably make it to 2028 with no problem. 2024 is only 9 years away. What's after that? Is anybody thinking about it? Are we really willing to gap our presence in low Earth orbit? Before we talk about what's next, let's talk about the current value of ISS. We're going to talk about research and technology, a little bit about what I call the astronaut's toolkit, or the Mark Watney effect, and then ISS as a deep space proving ground. I need to go back. How do I do that? Somebody has to do that for me. The other back. Back? Back. There's one button. It's a forward button. There we go. Okay. Now go forward. Thank you. You passed the test. Let's talk about biotech and research on the Duchenne's muscular dystrophy in the top left. Japanese scientists were able to identify a previously unknown water molecule. This is a real interesting research project. The way the crystals grow in space, you're able to actually disassemble them and look a little bit closer into what creates them. And we found in a protein an unexpected water molecule. We think that that water molecule might unlock a part of the cure for Duchenne's muscular dystrophy. It's the most prevalent form of muscular dystrophy and affects over 1 in 3,600 boys. Over 50,000 young males in the United States today. The average life expectancy is 25 years and there's no cure. Developing drugs using this technology take about 10 years to research and obtain a patent. Worldwide, the research efforts in molecular and cell biology to treat and cure human diseases and disorders have exceeded $700 billion annually. On the upper right, Amgen. FDA's approved Amgen drug, democinab, in 2010, is used to treat postmenopausal osteoporosis and subsequently for treatment of bone metastases. Both were developed in partnership with the ISS science teams. This drug is a $1.2 billion a year venture. Growing food in space. This was big in the news back in August. Astronauts grew a couple of leaves of lettuce, had a big celebration and ate it. Very interesting. But what was more interesting was how they grew it. They actually instrumented the lettuce leaves. So the lettuce determined when it needed to be watered and turned on the watering system. On the bottom right, astronaut Scott Kelly has just reached his halfway point, or just passed the halfway point of his one-year mission to the International Space Station. The journey to Mars will be 6 to 9 months. Medication and exercise will help alleviate the effects of the long journey. By the time Scott gets back, he'll effectively made the trip. With this research, we'll be able to prove that a journey to Mars is physically possible when it comes to how the body will be affected by the microgravity environment. Of course, interstellar galactic radiation is another issue that we really need to tackle, and there's work being done there as well. One of my favorites is the ISS Environmental Control System. If I can just take a minute to, this is actually an amazing system, and it's relatively simple. You know, humans produce stuff. 2 of the 3 things they produce are water in the form of water vapor from an exhalation and urine, and the other is carbon dioxide. Oh, yeah, sorry. If you take those constituents, we filter the water through a very porous filter, and we separate the carbon dioxide. In the CDR, the carbon dioxide separation rack on the ISS, we separate the carbon from the oxygen. After we create the water, the clean water, we use a process to disassociate the hydrogen from the oxygen. We take the carbon from the carbon dioxide, combine it with the hydrogen that came off of the water, and create methane gas. And methane gas is also a form of rocket fuel, but right now we inject it overboard. And in exchange for all that, we get what we and breathable oxygen. These systems are essential for the trip back and forth to Mars. The system relies on a set of organic and ceramic membranes with holes just 1/10 of a thousandth of a millimeter, 1/10,000th of a millimeter in diameter, which is currently 700 times thinner than a strand of human hair. These tiny pores can filter out unwanted compounds in water, including nitrate, a problem pollutant that comes from agricultural fertilizers. The Martian transit habitat will have an ISS-like water recycler. The ISS version produces several liters of fresh water daily using yesterday's urine and air conditioner condensate. Water, of course, is one of the most precious commodities in space because we need individually about 2 liters per day. It's heavy and it's difficult to haul into low Earth orbit and then propel to Mars. There's no filling stations between here and the red planet. And under the assumption that we can extract water from the Martian soil, we'll still have to traverse a 200 million mile desert before we hit the next oasis. A 5-person crew traversing the 6-month void between here and there will consume 1,800 kilograms of water. Given that it's practically impossible to launch all of that, The crew will effectively drink and re-drink that water many times over. And if the recycler breaks, we'll have to fix it. So let's talk about the astronaut's toolbox. Things are going to break on the journey to Mars. Our astronauts must have the tools and the experience to fix these life-saving systems. Apollo, Shuttle, ISS, all had toolkits. They've bypassed clogged drains, they've freed stuck doors, they've jumpered bad connections, and they've repaired torn solar arrays. Things that we have fixed in space include a watch, eyeglasses, exercise equipment, a parachute, and again, I call this the Mark Watney effect. What do we need, or why do we need tools in space, and how do we use them? On Mars, there's no help from mission control. There's a perilous time delay. You're essentially on your own every minute of the way. This video I pulled down off of YouTube. This is actually the modern day version of Mr. Watney, and it's Don Pettit. He's one of the brightest guys I know, and he never balks at a challenge. He had to replace the watch stem on his watch, and you see just the tricks of dealing with some of the small things like the screws on board was really quite an interesting experience. What I don't have a video of, and I thought was also outstanding, is an attempt to solder in space. Something simple like solder. We found that when the solder melted, the flux percolated to the surface of the solder and it began to vent. And it vented in a propulsive fashion such that the solder ball, the flux ball spun around the solder to the point that the test couldn't be conducted until the flux evaporated away. It was really interesting. A presence in LEO is critical. Again, assuming the lifespan of ISS of 2028, when will we provide an alternate destination? Aerospace development programs have not distinguished themselves for coming in under schedule. If we want a replacement by 2024 or 2028, someone should be working on it today. Ideally, we'll have an overlap in low Earth orbit capabilities as we transition from the ISS to whatever is next. And we want to do this because the knowledge gained is perishable. And the lessons learned that we're learning today quickly become diluted without constant reinforcement. We also want to do this because low Earth orbit destinations are essential to sustain the business model for commercial cargo and crew carriers. Without a destination, there's no business. Also, proving technologies required for the long trip to Mars may take years of confidence building in these technologies in low Earth orbit. Without a platform for testing and proving, there is much risk. To justify the business model for commercial entities to invest in an alternate low Earth orbit platform, there has to be a plan and associated funding. Bigelow Aerospace will soon launch the Beam, an inflatable module that will spend some time attached to the International Space Station that will test long-term exposure of inflatables and their suitability for long-duration space operations. The BE-330 is an amazing platform that Bigelow is building, but much development remains. Boeing, Lockheed, and Orbital have NASA contracts to study potential habitat architectures for Orion crews in cislunar space. Can we leverage these for a low Earth orbit habitat? And who will pay? The government should still play a role in LEO, including bearing some of the financial cost, perhaps using the same model as the commercial crew program. Specifically, NASA determines a level of service it needs to satisfy its low Earth orbit scientific research objectives and awards contracts incrementally under a Space Act agreement to establish the right venue. The final requirements are iteratively determined such that the NASA cultivates a fee-for-service platform for continued research while stimulating growth for other potential customers, including private research. International participation for countries who don't need nor want the infrastructure of a full orbital laboratory is also a potential investor. Big players in aerospace, of course, should invest. In an effort to stimulate deep space capability across the aerospace industry, last year NASA released the next the Next STEP program. That's the next Space Technology for Exploration Partnership Program. It was a broad agency announcement through which NASA has increasingly embraced the public-private partnerships to expand the frontiers of knowledge, capability, and exploration of space. Pharmaceuticals and medical industries should invest. Amongst others, CASES has been stimulating market to zero-G payloads. We'll hear about that from Greg Johnson tomorrow. Again, a smooth transition to follow-on LEO platforms. These companies are key to retaining a steady stream of research. International investment. Partner countries and or international commercial investors should lay their stake as well. At the end of the ISS life, we'll be at a world population of almost 8 billion people and rising. To sustain this growth, we need to look outwardly as well as in. How do we start now? Should we consider giving investors a role in ISS today so we have a basis for the business case for the next low Earth orbit habitat and destination? The transition should be an overlap. We should not gap this service. A journey to Mars is clearly a marathon and not a sprint. A sustained presence in LEO is an element of the marathon. Consider a model where private industry forms the supply chain for low Earth orbit, continually providing a fresh supply of research and provisions for stepping into cislunar space. If Everest is Mars, then a sustained LEO presence is base camp, and private industry are the Sherpas. Like Megan Trainor said, it's all about the base. That's all I have. Thank you.